Right, let's do some physics. This time it's triple higher, paper 2, it's SP14, which is the particle model. But for anyone studying physics, the particle model is just anything to do with particles, density, energy, changes of state, gas temperature and pressure, and volume, that sort of thing. So these are questions that will come up on your GCSE Physics exams. Now there's 33 marks worth of questions here. These questions have been taken from the last 3 years of papers. So that tells you that they're fairly popular. In other words, you're probably going to get a few questions to do with this on your exam papers for any year that you sit. Question 1. A student uses the apparatus in figure 3 to determine the specific heat capacity of water. Underline that. State the measurements needed to calculate the specific heat capacity of water. Right, well I always base my explanation on the calculation. So the calculation for specific heat capacity is the change in the heat energy is equal to the mass times by the specific heat capacity times by the change in temperature. So if we just rearrange that, so therefore C, the specific heat capacity, will be the change in the heat energy divided by the mass times by the change in temperature. So in order to calculate the specific heat capacity, we need to know the energy that you're putting in. So that's why they've give you a joule meter. You'll need to know the mass of the water because you're trying to get the specific heat capacity of the water. And the change in temperature. Well, in order to get the change in temperature, you need to know the initial temperature and the final temperature. So that's the energy, the mass of the water, initial temperature, final temperature, and that'll get you the 4 marks. Part 2. State any 2 ways that the apparatus could be adapted to improve the procedure. Right, let's have a look at it then. Right, well the energy that's going into the water, some of it might escape because there's no lid on. So I'll put a lid on it. And the immersion heater is not fully submerged into the water. So some of the energy that you're supplying won't go in the water. It'll end up getting lost to the surroundings. You could put a glass beaker around the polystyrene cup in order to support it, stop it from getting knocked over. Polystyrene's not very heavy, is it? If that's easier for you to remember. Or another easy one might be to put insulation around the cup. I've just said there, put the polystyrene cup into a glass beaker to support it, stop it being knocked over. Question 2. Figure 2 shows a rubber tube that can be used inside a bicycle tyre. The tube is inflated with a bicycle pump. The air inside the tube exerts an outward force on the wall of the tube. State the angle that this outward force makes with the wall of the tube. Right, well, whenever you've got one of these pressure equals force over area type of questions, the force always acts at 90 degrees. So in other words, sort of straight at the wall. You could say perpendicular. Part 2. It takes 4.8 litres of air from the atmosphere to inflate the empty tube to a pressure of 400,000 pascals. Atmospheric pressure is 100,000 pascals. Calculate the volume of air inside the tube. Assume the temperature of the air inside the tube is the same as the temperature of the air outside the tube. Use an equation selected from the list of equations at the end of this paper. Right, so what you want is this equation. P1 times by V1 equals P2 times by V2. Right, so let's make sure we assign the correct values, because that can be a bit tricky. So let's reread the question. It takes 4.8 litres of air from the atmosphere. Right, so if we say 4.8, that's our volume 1. And if it's from the atmosphere, it says that the atmospheric pressure is 100,000. So that'll be our pressure 1. Now it's going to inflate an empty tube to a pressure of 400,000 pascals. So that'll be our pressure 2. So that's the pressure we end up with. And it's asking, can you calculate the volume of air inside the tube? So what will the volume be at the end? Volume 2. Right, so volume 2 is what we're looking for. So if we rearrange the equation to get volume 2, and then if we pop the numbers in, and that will come out as 1.2 litres. Now let's just take a minute to make sure you understand that. So what we've got at first, because we've got a low pressure of 100,000, you've got a bigger volume. Now you can see, look, the pressure is going to get 4 times bigger. It's going from 100,000 to 400,000. So if the pressure gets 4 times bigger, that's going to make the volume get 4 times smaller. Because the more that you squash something, the smaller it gets. So yeah, because the pressure got 4 times bigger, the volume got 4 times smaller. I hope that helps. Part 3. When a bicycle pump is used to inflate the tyre, the air of the bicycle pump gets warm. You should ignore any effects of friction in the pump. Explain why the air in the bicycle pump gets warm. Right, it's always the same answer. When you're pumping up the air, you're doing work on the air. Now, if you can remember the equation, you should always back it up with the equation. So work done equals force times by distance. Remember, when work gets done, energy gets transferred. So the gas particles will gain energy, and the type of energy they'll get is kinetic energy. And basically, the faster the particles are moving, the higher the temperature is. Question 3. Figure 1 shows air inside a cylinder with a movable piston. The piston is pulled a little way in the direction of the arrow, so outwards, but stays inside the cylinder. Which of these increases? The mass of the air inside the cylinder? Nope. The mass of the air will stay the same. Whatever the mass of the air was at first, just because you pull that plunger out a little bit, it doesn't mean that you've got extra mass in there. There's no extra mass going to get in there because it's a sealed system. So that's wrong. Remember, we're looking for what increases. The rate at which air particles collide with the walls of the cylinder? No. If you are pulling this plunger out, the rate that the particles hit the walls will decrease, not increase. The volume of the air inside the cylinder will increase. Yes, it will. If you pull that out there, these little particles, remember, a gas will expand to take up the volume. So the volume will increase. So that one's correct. The pressure of the air inside the cylinder will increase. No, that's wrong. The pressure comes from the number of collisions per second and the force that they put on the wall. Pressure equals force over area. So the pressure will end up decreasing. Number 4. A beaker contains 0.25 kilograms of water at room temperature. The beaker of water is heated until the water reaches boiling point, 100 degrees C. The specific heat capacity of water is 4,200 joules per kilogram degree C. The total amount of thermal energy supplied to the water is 84,000 joules. Calculate the temperature of the water before it was heated. Use an equation selected from the list of equations at the end of the paper. Right, Well, what we've got is the mass of the water. We've got the final temperature of the water. We've got the specific heat capacity C. And we've got the total amount of heat energy or thermal energy, which is delta Q. So the equation that links all of these things is the change in the thermal heat energy equals the mass times by the specific heat capacity times by the change in temperature. So we're going to have to rearrange that to get the change in the temperature. So if I pop the numbers in, and that comes out as 80 degrees C. Now 80 degrees C isn't the temperature of the water before it was heated. That is the change of temperature. So remember, the change of temperature, it'll equal the final temperature, take away the initial temperature. And we want the initial temperature. So rearrange that equation. So the final temperature was 100 degrees C. And it changed by 80. So if we take the 80 degrees C off, that'll tell us that the starting temperature must have been 20 degrees C. If you just put the answer down as 80, you'll probably only get 2 marks instead of 3. Part 2. The heating continues until 0.15 kilograms of the water has turned into steam. The thermal energy needed to turn the boiling water into steam is 0.34 megajoules. Calculate the specific latent heat or vaporization of water. That's what we call L. Use an equation selected from the list of equations at the end of this paper. So we've got mass, change in thermal energy, and latent heat. Now, very often, if you're struggling to find what equation to use, have a little look at the units, and that'll tell you what you need to do with these values. Our eventual answer needs to be in megajoules per kilogram. Oh, look, that's in megajoules, and that's in kilograms. So you just literally need to do the 0.34 megajoules and divide it by your 0.15 kilograms. Good, eh? The actual equation is delta Q equals M times by L. So if I did rearrange that to find L, we'd just be doing delta Q over M, which is basically what we've done there anyway. And that equals 2.26 recurrent. Or we can round that up to 2.3. If you are going to round it up, just make sure you put the full number up the top there. Now, looking at the units that they wanted in also helps you to understand whether you need to convert it or not. It was absolutely fine to leave the joules in megajoules because they wanted the answer as megajoules per kilogram. Part 3. The graph in figure 13 shows how the volume of 1 kilogram of water changes with temperature. Describe how the density of water changes with temperature over the range of temperature shown in figure 13. Calculations are not required. Right, they've highlighted density, and that's because they haven't given you density, they've gave you volume. So in your mind, you're going to have to convert volume into density over that range of temperature. Now, because they've given you the units, they want you to talk about it. Now, it's only worth 2 marks, but I can see 3 significant things. Talk about what's happening between here and here. Talk about what's happening here. And also talk about what's happening between here and here. Because there's definitely 3 significant parts of the graph. Now, what equation do we know that relates density to volume? Well, we know that density equals mass over volume. Now, they're not interested in mass, so therefore, let's get rid of mass. What we know is that density is proportional to 1 over the volume. So in other words, as the volume increases, if this number here was to get bigger, this number here was to get littler, and vice versa. Now, the volume at first is getting smaller. So if the volume is getting smaller, the density is getting bigger, and quote the values. So between 0 and 4 degrees C, the volume is decreasing, which means that the density is increasing. Let's just make sure you understand that. So at first the volume, let's say the volume's that big, and we've got 1, 2, 3, 4 particles in there. Now over here, what's happened is the volume has decreased, so the box needs to be littler, but it's still got the same amount of mass in. 1, 2, 3, 4. Look at the density. Density is how close the particles are. The density is very high because the particles are really close. The density here was lower because the particles were further out. Look at this bit here. As the volume gets much, much bigger, I've still got the same number of particles, 4, but look at how much space they've got. So here the density is very low. And we just need to write that down and we'll get our marks. At 4 degrees C, it's at its highest density. And then from 4 degrees C up to 11 degrees C, the density decreases. And there we go. Calculations weren't required, but it still was good to look at it mathematically. That just means that the density increases if the volume gets smaller. Question 5. Another student decides to melt some ice. The student melts 380 grams of ice at 0 degrees C. Right, well, immediately alarm bells are ringing because that's in grams. And I'm looking over here and that's in kilograms. We're going to have to convert that into kilograms, so that's 0.38 kilograms. Remember, to convert from grams into kilograms, you divide by 1,000. And that's because there's 1,000 grams per kilogram. The specific heat of fusion of ice is 3.34. That should be times 10 to the 5 joules per kilogram. Calculate the thermal energy needed to melt the ice. Select an equation from the list of equations at the end of this paper. Well, whenever there's a change of state, the amount of heat energy required will be the mass times by, in this case, the latent heat of fusion. So bang the numbers in. I always put the units on because then you can tell if there's any problems. At this point here, if I suddenly spotted, whoops, that's in grams and this is in kilograms, then I'd realise my mistake and correct it and make sure I got all my marks. And that equals 126,920. 126,920 joules. Question 6. A student measures the density of glass. The student has a bag of marbles, all made from the same type of glass, a weighing balance, a plastic measuring cylinder containing water. Describe how the student could find, as accurately as possible, the density of the glass used for the marbles. Well, as I say to my students, you should base the explanation on the calculation. So first of all, if we're going to get the density, let's start with the equation. Density equals mass over volume. Now, the thing is it says get it as accurately as possible. So what they mean, instead of just getting the mass of one marble, let's get the mass of multiple marbles. And when they're saying it's a weighing balance, what they really mean is a mass top pan balance. But they probably didn't want to use the word mass, otherwise that gives the game away, doesn't it? So let's measure the mass of 10 marbles. Now, if we're getting the mass of 10 marbles, we need to get the volume of 10 marbles. Now, we'll end up getting the density of one marble because we're doing the mass of 10 marbles divided by the volume of 10 marbles, just in case you were worried. Now, we'll get 1 mark for saying how to get the density. We'll get 1 mark for saying how to measure the mass of 10 marbles. And we'll get 1 mark for saying measure the volume of 10 marbles. We need to give a little bit detail about either this or this. Now, it did say that the marbles were in a bag. So we could say subtract the bag. Now, if you don't want to say that, what you could say is how to get the volume of the marbles is basically, if we have got this measuring cylinder, if we just fill it up to halfway with the water, and then what we'll do is we'll pop the 10 marbles in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what will happen is when we put the marbles in, the volume of water, blah, 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 will go up. So our volume, if we say that's volume 1 and that's volume 2, the volume of the marbles, it'll be V2 take away V1. Now, if you don't want to draw that picture, you could just simply write it like this. Put the marbles into the water in the measuring cylinder and measure the change of volume. That's the volume of the marbles. Question 7. A student investigates how the volume of a gas changes when its temperature changes. Volume, temperature. The diagram shows the equipment used and the length of the trapped gas at 25 degrees C. Right, so what they've got is this tube here, and they've got a little bit of liquid at the top of this volume. As the temperature of this water bath changes, it'll have an effect on the volume of this air, and it'll expand, and it'll move this little volume of water upwards. Use the scale to estimate the length of the column of trapped gas. So from there, right the way up to there, it looks to me to be just before, that's 10, 11, 12, 13, 14, 15. It looks like it's just below 11. So I'll say a 10.8. Mind if you were to just say 11, that would probably be fine as well. And that's in centimetres, which was what they wanted. Part 2. Complete the sentence by putting a cross in the box next to your answer. The cross-sectional area of the capillary tube is that many centimetres squared. The volume of the column of trapped gas at 25 degrees C is about... Right, so everything was at 25 degrees C. So to get the volume, you do the length times by the cross-sectional area. So if we do 1.94 times 10 to the minus 3 centimetres squared, and we said it was 10.8 centimetres, that comes out as 0.020952, and that'll be centimetres cubed, because it's centimetres squared times by another centimetres, which gives us the cubed. Right, let's pop it into standard figures. So that's 2.0952 times 10 to the minus 2, because there's two nothings there. So that'll be this one, B. 2.1 times 10 to the minus 2. Well, ours would round up to 2.1. Part B. Describe how the average kinetic energy of the particles of the gas changes as the temperature of the gas changes. So we're looking for the link between average kinetic energy and temperature. Right, well, if you know anything about absolute zero, if you've got temperature along the bottom in kelvins, and you've got your average kinetic energy up the side, when the temperature gets down to zero, so that's absolute zero, the kinetic energy will be nothing. And as the temperature increases, the average kinetic energy also increases, and it's directly proportional. Make sure you say when the temperature is in kelvins, and you'll get all 3 marks for saying that. If all you said was as the kinetic energy increases, the temperature increases, well, you'll just get 1 mark for that. If you say that they're directly proportional, you get 2 marks, but you'll get your 3rd mark for saying they're directly proportional when the temperature's in kelvins for your 3rd mark. Question 8. A student uses the apparatus in figure 3 to determine the specific heat capacity of water. The student decides to measure the temperature of the water every minute while it's being heated. Figure 4 shows a graph of the student's results. Predict the temperature of the water if the heating continues up to 8 minutes. Right, well really, this is just a question to see if you can understand graphs. Now if I've got a steady hand, I just need to basically follow that line, create a line that comes up here like that. I think that looks about right there, that looks about right there, and that looks about right there. So I'm going to say 100 degrees C. Now the thing is you know that water doesn't really get above 100 degrees C, not when it's heated at standard pressure. Mind the water could be impure, so the temperature could be slightly higher or slightly lower than that. But going off the graph, that looks to be right. And again, there will be a little range that the examiner will accept. Right, and that's the last question. So well done. All of this time and effort that you're putting into your own personal development will definitely increase your grades. There'll be more videos like this coming up. Make sure you've subscribed to my channel, smash that like button. Apart from that, work hard, be nice, and bye for now.